你的考卷还没有看呢，等下你要看吗？办公室。Testing。Testing. Okay. Good afternoon to everyone. Um, Thanks for the prompt. Any question on the assignment or not? You want to ask? Huh? No? Yeah. Does limit exist for integer? What do you mean? Limit only work for function and sequence, right? Okay. So what do you mean by integer? Integer sequence? Sequence of integer? Hmm? As this, I mean, you need to consider sequences or functions. Integer value function, maybe. Hmm. Integer value function, I guess, doesn't exist unless, yeah. So this week we have assignment, and then next week we got presentation on Tuesday. Right? So Tuesday, and I put the venue out already. It's A5G01. Is it? You check the announcement. Maybe I should send out announcement as well. I put on the Moodle week, so it's week 12. Huh? 7 to 9 evening. So there will be one general topology master student joining as well for the presentation. So we do the two presentation together for two classes. Tuesday, huh? Sorry? It's just for master only. Undergrad don't have. Yeah, yeah. So there's only one master student there, so he's the only one. Yeah, A4, sorry, A5G01. Yeah, 7 to 9. Okay, the format is almost the same as last time, but this time I gave you a little bit more time. Okay, but I don't think you need too much time. Hey, by the way, you guys know NVIDIA or not? Huh? NVIDIA. You know NVIDIA? Yeah, I see a lot of NVIDIA because there's an AI hype. So NVIDIA is the what's that? The computer graphic card. Yeah. Is it graphic card? Yeah. GPU also GPU. So this NVIDIA CEO is a Taiwanese called Jensen Huang. You guys should watch his keynote presentation. I think it's pretty good. It's very good actually. Maybe later we can share a little bit of it. There's another company called the Super Microcomputer, SMCI. Yeah, recently the stock of this tool is quite volatile. That company is also a Taiwanese CEO. His English is not as good, but they are good friends to each other. So they both go to the keynote in Taiwan. They make a keynote in Taiwan, and then later I show you how they two interact inside the keynote. Okay. Yeah. You've got chance. Yes. 7-4. Uh-huh.
Looks like for this,
Yeah, you just keep going.
so the hint that says start defining big F and X, right? But the term, the function inside use X and it is supposed to be just X.
Where? The first one?
Yeah.
Let me think. Should it be just X unit or S temp?
Yeah, instead of X and should it be just X?
See. Yeah, I think should be X. Should be X. Anything else? Yeah, I think should be X. Should be X.
Sure.
X. Huh? Yep.
Also,
Wait. Let me check again for sure. So XM. Let me check. Yeah, I think it's X. X. Yeah. Yeah. This proof, right? This proof you can try and read the course book is that fixed metric. You can try and refer to the fixed metric, the section on the Cauchy mean value theorem. Again, there's a similar theorem to this one, and you can refer to that. Yeah.
for the last part, there's a sentence like then proof by induction for given X in it. Like there exists X and between A and X. It is supposed to be X and C.
Which one? X, A, B cannot be C. This that. Which part?
The last group, like the last sentence is there exists X and between A and X.
There exists X and B.
Is it supposed to be between X and C?
Let me think. A and X or X and C. X and let me think. Oh, because here I wrote X and C. Uh, let me think again. What is the C here? Let's see the point. There. And then that. And then XM is divided by X and C. It's in between X and C. Maybe. So that it's between X and C. A and X. Single slide. Then what's the difference between A and X and C? Okay, I think it's S and C. Should be S and C, yeah. Should be closer to C instead of closer to A. Let me think. Check. Yeah, should be C and X. Yes, you are right. But the FM, let me check. Bit weird. Let me see. Should it be X or XM? What's the XM for some XM? Well, let me check whether this FMX is purposely XM. Because if I define XM also making sense because you are fixing X here and then you got to C here and then let me think. You should have some point in the middle using this Cauchy ring value theorem. Okay, let me see. Okay, I think should be X, should be X, should be X. Yeah, should be X. Yeah, just X. Okay, this one is just X. I will change the notation later, the typo. This should be X. And then the last part here is the last hint here is C and X instead of AX. Okay? Yeah. Now, hopefully the previous few are quite straightforward, but the hardest one is supposed to be this one. There are quite a few notation to learn here. A bit more complex than the fixed matrix theorem. Yeah. Okay, because in fixed matrix they only deal with the last term, but in this case we deal with the whole Taylor series. Okay. Yeah. I mean, if you still have problem, we can talk again tomorrow if you want. Yeah. Maybe I can even tell you how to do it if you really stuck on this one. Okay. Is that okay? Yeah. If you're really stuck, then we can briefly discuss about it and then see what about it. Okay. Okay. So if you really stuck, and then tomorrow maybe we will briefly run through this thing. Okay. Any other question you want to check with me? Any other question you want to check? Okay. All right. So let's start. Okay, so we will continue with the book's integral. Book's integral. Okay, so remember how we introduced the book's integral? What's the tool that we use to estimate area under the graph? What's the tool? Rectangle. Okay, so we use rectangle. We use rectangle. In particular, we define upper sum and lower sum. Okay, but to do upper sum and lower sum, what's the first thing you need? Okay, let's say our function defined from a closed interval from A to B. Okay, so what's the thing we need to build upper sum and lower sum? Huh? We got function already, right? So what's the other thing we need? Sorry? Before defining upper sum and lower sum, what did we define? Huh? width. So P, what's the word start with P? Partition. Okay, so we define the partition of AB. All right. So for example, let's say we take this particular partition here, ACB, okay, of AB. So you can see that what's the upper sum here? So the upper sum in this case would be the speed here. Okay, so we partition AB into two parts here. So we have two upper sum, looks like this. Okay, and we can consider the lower sum as well. Okay, lower sum. So how does the lower sum looks like? The lower sum is something like the following. Okay. So what can you see from this diagram? How do you compare lower sum and upper sum here? How do you compare upper sum and lower sum here? Which one is greater? Which one is smaller? Upper sum is always larger than the lower sum, right? Because in upper sum, how do we define? We use the supremum of f or maximum of f. If if the supremum is achievable. And lower sum we use infimum. Okay, so you see this purple one, the lower sum, right? I choose the infimum between the width, okay? Between the width of B minus C. Okay or not? So upper sum usually overestimate the area or underestimate? Overestimate the area, okay? Because your function maybe go below the supremum, you see? Okay. How about the lower sum? The lower sum always underestimate the area because your function might go above the infimum. Okay, then you miss out some of your area under the function. But what can we do to better estimate this area under the rectangle and area under the ground? What can we do? What's the last thing we introduced last week? What can we do? Can we make this rectangle better estimate our function or not? How? More partition, or we call it a refinement. Okay, so we can make our partition how to say? Cannot say smaller. We can introduce a final partition. Okay, so what do we mean by final partition here? So meaning we can introduce more points. Okay, more point into our partition. So for example, we can break it into, so we can break AC into AD and DC. And then CB break it into maybe CE and EB. Okay. And then what? What's the proof we proved last time? Okay. So if you consider this rectangle of AD, DC, CE, and EB, okay. If we just introduce this new final partition here, ADCEB, okay, with the same value of f, then this area doesn't change. But if we restrict, okay, the soup to AD, or restrict the soup to DE, or restrict to the soup of CE and EB, what can we see here? Okay, what can we see here? What's the upper sum of AD here? Does it change when you compare to AC? Does it change or not? I couldn't say upper sum, right? So okay, so the upper sum, okay, we get from AD and DC. Does it change when you compare the addition of AD and DC to AC? Does it change in this case here? Can understand what I asked or not? Does it change? Sorry, a little bit. You sure? Which part changed? AD, yeah. Okay, sure, good. So maybe we have a little change here. For example, right? Okay, very slight changes here. But what kind of changes is this? Increase or decrease for the area? Decrease, right? Okay, so you can see, for example, at CE, compare, okay, see the upper sum of CB and the addition of CE and EB here. You could also see that in the upper sum for EB, it also decreases. Okay, so meaning what? When you have refinement, the upper sum will decrease. Okay, how about lower sum here? How about lower sum? Okay, how about lower sum of AD, DC adding together compared to AC? Okay, how about this? So in AD case, the lower sum should be the same height. Okay, it's different lower sum but same height. How about DC? Where's the lower sum? You can see that the lower sum actually increase. Okay, you can see that the lower sum increase within DC. Okay, should I use this color? Maybe use white. Let's use white. Okay, let's use white. Okay, how about lower sum in CE? How about lower sum in CE and EB? Okay, so you can see that in CE, the lower sum is almost the same as the one in CB, and in EB, it is also almost the same. Okay? Yeah. So for refinement, your lower sum will increase, okay, or stay equal, and the upper sum will decrease or stay equal. Okay. So this is the last bit that we left last time. So let me make a remark here. So this is the thing we proved last time. So if Q is a refinement of P, then the lower sum of FP is less than or equal to lower sum of FQ, less than equal to upper sum of FQ, and then less than equal to upper sum of FP. Does it make sense? So can you see here, if I refine Q again, the two number will go into the middle. So you can see that the upper sum is like decreasing, the lower sum is increasing. Okay. So I mean, in the exam, do you still remember this question? So what happened to the what's the result of this kind of sequence that we have proven? The supremum of L is less than equals to the infimum of all these U. Okay, so the greatest one, the lowest upper bound of L is less than equal to the least or the greatest lower bound, okay, of U. Okay. Okay, so I mean, so from here, right, you can straight away deduce that if P and Q are any partitions of, let's say, on the domain that F defined, then LFP is always less than or equals to UFQ. Okay. I give you 1 minute. Can you show how do you deduce this corollary from this theorem? So this is a corollary, right? Meaning you can use the theorem above to prove it. Okay, I give you 1 minute. How to prove it? So the theorem above talk about refinement. Can you find a refinement or not? Can you find a refinement for this corollary here? Any idea? So to use theorem, the above theorem, you need a refinement, right? Okay. So can you build any useful refinement in this case? Recall what is partition. So let's say P is what? S A equals to the first term S0, maybe X1, to Xn, and the last term is B, right? How about Q? Q is also another partition, so let's use yi to denote it, y0, y1, to yn equals to B, and then, okay? So can you build some useful refinement? We can consider R equals to P union Q. And what is RP union Q? Let's say, give an example. So let's say we have a 0 to 1, okay, interval. And then let's say our P is just 0, 0.51, say, right? Q, maybe we can take 0, 0.25, 0.751. Then, if we take the union of these two, what do we get? Union of these two sets, what do we get? 0, 0.25, 0.5, 0.75, 1. So you can see that this P union Q, right, contain P and contain Q. So P union Q is a refinement for P and Q. Okay, so it is a refinement. So consider this union here, which is a refinement of P and Q. Okay, so since P union Q is a refinement of P and Q, right? So LFP must be smaller or equals to the LFR, right? But we know that lower sum is always less than equals to the upper sum for any partition. And this R is a refinement of Q. So meaning this upper sum here should be smaller than the upper sum of. Okay, so we're done. Okay, make sense? Does it make sense? Okay. Okay, good. So what we can see here, so a corollary again, let f be a bounded function. So bounded function meaning the supremum and the infimum we consider in the upper sum and lower sum will be achievable. Okay, there's a maximum, there's a minimum there. So we can consider the set of all lower sum. Okay, how can you comment about this lower sum? Any comment? Any comment about this set here? So if you talk about a set, right, you want to see whether you define an empty set or not. So this is empty or not, this set? Is this set empty? No, right? Because you can just consider the partition AB. And then what's the infimum there? Because this function is bounded, there's an infimum there. Okay? So you can simply consider the partition AB here, non-empty. Moreover, this set is what? There's an inequality we established just now, right? All the lower sum should be bounded above by the upper sum. Okay. So in particular, this set is bounded above. Okay. And this set is what thing is inside here? Lower sum, right? But lower sum is what? Is a function or a number? Number is a real number. So this is a set of real number which is not empty and bounded above, meaning what? Completeness axiom says what? Every non-empty set of real number that is bounded above is or has what? Has a supremum. Okay, so this guy has a supremum. Similarly, you can define the set of upper sum. Okay, you can define the set of upper sum. It's also non-empty. It is also bounded below. Okay, bounded below by the lower sum. Okay, bounded below by lower sum. It's bounded below. Okay or not? Make sense? So in this case here, UF will have a minimum or infimum. Okay, infimum. Can't say minimum. Maybe it's not achievable by a partition. Okay, so we will define here. So it makes sense to define. So similarly, we must have a bounded function first. Okay, and then we consider all. Okay, all collection of all partition of AB. Okay, so we will define that the upper integral of F. Okay, so what's the upper integral here? Is defined to be, we will write it as UF. Okay, UF. No P here, you see? So upper sum, we define using a partition. But here, upper integral, we don't care P anymore. Okay, why we don't care P anymore? Because we are taking infimum of all upper sum, UFP. Okay, we consider all partition and then take the minimum or take the infimum, sorry. Okay, minimum may not be achievable. Does it make sense? Okay, make sense? Okay, and similarly, we can define the lower integral. Okay, lower integral. So what's the lower integral of F? It is defined to be LF. Okay, LF here, there's no P also. Okay, why? Because we define it as a supremum of all possible LFP. Okay, we look at all possible LFP and then take the supremum. Does it make sense? Okay, that exists because by the completeness axiom. Okay. Any questions so far? These two have to make sense to you first, then yeah. Otherwise, you will get lost inside the proof later. Okay. Okay, good. Next, we have a lemma, a very slight exercise for you. Okay, to think about what is LF and UF. Later, we will use this lemma to prove something also. So note that the function we consider so far are all bounded. Okay, no continuity, just bounded. Why bounded? Because when we define upper sum and lower sum, right, we use what? supremum of f and infimum of f. If it is not bounded, what happened? What happened to the supremum and infimum? Maybe go to infinity or maybe negative infinity. Okay, that those numbers we don't want. Okay, so we want to have some finite number here. So it is bounded, right? Say fx is bounded below by little m and bounded above by big M. Okay, for all x in AB. Then what? Okay, then we have m of b minus a less than or equals to LF less than or equals to UF less than or equals to MBA. Okay, so stay at this lemma for a moment. Okay, which inequality you think this is easy to see? Which inequality you think it is easy to see? Sorry? Middle one is easy to see. Why? Supremum of LF should be less than or equals to infimum of what? UFP, right? This is easy to see because I asked you to do in an exam. If not, then you cannot see. You know, it is actually very hard to see. I give you how many points for that exam? About 10 or 15, I don't know. Actually, not very easy to see. You think it's easy to see because I make you do it. Okay. Actually, the easiest to see one is the left and the right one. Leftmost and the rightmost. Why? Why is it easiest to see? What is B minus A here? What's the partition they consider there? What's this part here? Okay, let's comment here by the exam question. Okay, so what's this? How can you realize this as a LF of some P? LF of what? Yes, this is just LF of the partition that contains A and B, right? Right. Okay, meaning you just consider the starting point and the end point. This is the partition that you consider. Okay, A, B, the whole thing. Okay, so what's the infimum there? Obviously, your function is greater or equals to M. So the infimum of fx inside AB should be M. Okay, because this guy is just infimum of fx, where x is in AB times what? Times B minus A. Okay, like that. Similarly, on the right hand side, what do you get? That one is U of F. What partition? Also just the partition containing the point A and B. Okay. Because this is literally the sup of fx, where x is in AB and times B minus A. There's only one width you consider there. Fair enough. Okay. Yeah, actually, yeah. So all the other partition inside LF and UF should be a refinement of the partition of AB. Okay. Does it make sense? Okay. Any question for this one? Yeah.
It doesn't change like the overall result, but like technically the lower sum with AB is less than or equal to the inf, right? Because like M and the small and big M may not necessarily be influence supremum of X.
Oh, okay. So, I get what you mean. So, I mean, wait, let me think. Correct. So, I mean, okay. So you say that, sure. So this part here might not be equal, right? So this part here might not be equal. Why? Because if the infimum of fx is m, right? Maybe I can reduce this lower bound some more. Correct or not? So I mean, okay, let me put here. So if m less than or equals to fx and less than or equals to m, then what? Then the infimum of fx of x in AB should be greater or equals to m. Okay, this is what I want to say. And also, the sup of fx and x in AB could be less than or equals to m. Okay. So might not be equal, but we still have the order preserving here. Let me see how to preserve this order. So here, greater than this one. But what we established just now is because AB is one of the partition, right? LF consider all partition, okay? So you see, this B minus A here, this partition, right, is we can say as a closest one because you don't really haven't refined it, right? B minus A. You consider the whole partition here. So inside here, you could have more refinement, right? So we could have this one. So let me do like this. Okay. So okay, let me write down here. So okay, let's write down. By the way, please ask question because we need to go a little bit faster now because we spend a lot of time in the basic. So hopefully you can grasp faster. Okay. So first of all, does everyone agree with the first inequality here? The first inequality here. Does everyone agree? Can agree? Okay, good. So next, we want to establish this second inequality here. How do we establish second inequality here? Remember that LF, we consider the infimum of all partition. Okay, consider LFP for all partition. But what's this B minus A partition here? This is the most basic partition, right? Any other partition inside LFP here should be finer than this guy. Correct or not? Maybe you have yeah, maybe, yeah, okay, it's finer. So meaning what? Meaning this supremum of LFP should be greater or equals to this m this increment of fx minus multiply b minus a. Does it make sense? I mean what I say. So if you don't understand what I say, please ask. Okay. Yeah. So this is the same story happening in the UFP part. Okay, UFP part. So we can see that m times b minus f should be greater or equals to the upper sum of f using the partition AB. Okay. So if you want to show that mb minus a is greater or equals to UF, you just need to make sure that UF of AB is greater or equals to UF. Okay. So the same story here. In UF, what do? We consider the infimum of all partition. But AB is one of the partition. Okay. So all the other partitions should be a refinement of AB. So your UFP must decrease. Okay. In particular, the infimum should be less. Does it make sense? Okay or not? So very important, you want to get the idea first, and then you try and write it up. Please get the idea because we will try and reduce writing a lot of proof here because proof is quite consuming. I'm consuming. Yes, question. Why the M again? So this little m and big M is the number that bound fx for all x inside AB. Okay, but it doesn't guarantee that infimum of f is the little m or the supremum of f is the big M. Okay, it's just that It's just two numbers that bound the value of these two. Right or not? For example, what? For example, okay. So for example, since Since f is bounded, right? Infimum of fx and supremum of fx exists. Okay, exists, then it is true that infimum of fx is less than or equal to fx and greater or equal to sub fx. But you can also add a random positive number such that fx is less than inf of fx, maybe minus r fx, and greater than sub of fx plus r, right? So then you can set this as your small m and beta great M respectively. Okay. Yeah, so this is the possible problem that happened. So we cannot say that this LFP actually equals to MB minus A. Does it make sense? Okay. For question? No? So far? Okay. Please ask, please ask. Don't wait, because we can wait for you if you ask. If you don't ask, then we don't know how to wait for you. Make sense or not? 合理吗？对，有问题你就提出来因为你不提出来，我不知道你有问题。有问题我们可以一起解决。好 ，Okay, good. So next, so what have we seen? What we have seen is LF is always less than or equals to UF. Okay? This is what we see. Okay, we have proved that. Is it possible that LF is greater or equal to UF or not? Is it possible? Who say? Why not? And then? Or strictly less than. But it could be the case that they're equal. Okay, it could be the case that they're equal. Okay, remember here we are taking one of them, we are taking supremum, one of them we are taking infimum. Although in every partition, they have to be less than or equals to, but once you take supremum and infimum, remember there's a case, for example, what is the infimum of 1 over n? 1 over n is always greater than 0, but when you take infimum, it becomes 0. Okay, so it could be the case that they're equal. So what happens if upper integral and lower integral equal? Then we will call this function integrable. Okay, so this is the first instant you see integrable. Okay, so we will start with a bounded function again, because we want our upper sum and lower sum to be finite. Actually, this is what we call the Darboux integrable. Okay, the Darboux integrable. And later we will comment about Riemann integrable. So if a bounded function is the Darboux integrable if the upper sum and lower sum coincide. Okay, if they're equal. Okay, so how to show a function is the Darboux integrable? What do you need to do? Hey, hello. Only one equation there. What do you need to do? If you want to show a function, the Darboux integrable, what do you need to do? Sorry? Compare it. What's the name? We give this guy a name, right? Okay. I don't know, but Asian typically don't like to remember people's name, you know. If Australia, when we study there, the first thing we shake hand, we say, what we say is our name. Yeah. But Asian will say, hey, that one, that guy, the red hair guy. The red hair guy, or the tall guy, or the skinny guy. Never remember the name one. I don't know why. Okay. So what's the name? What's the name of LF? Lower sum. Lower integral. UF, upper integral. Okay, how do you define lower integral and upper integral here? Lower integral is the supremum of lower sum. Upper integral, infimum of upper sum. Okay, all possible partition here. Okay, and thus, then we will denote the Darboux's integral, or simply integral of f on AB by the integral sign ABF, or sometimes we write integral of AB fx dx. Okay, I think this one is more familiar to you. It's what? It's just LF or UF, because they are the same already. Okay, just take LF or UF here. So you see, when we define integral, right, we always remember our domain here. Okay, we remember our domain. Or actually, this is what you guys call the definite integral. Okay, definite integral. Okay, we haven't defined the integrate fx yet, not yet. Only with domain now. You only know how to integrate function with domain. With a closed domain, I mean. Okay. Right. So one remark here is, you see, we start with a bounded function to be integrable. Okay, meaning this LF and UF should be finite. That should be finite number. Another question is, it is sensible to ask, can I throw away this boundedness? Okay, so if you throw away this boundedness, what happens? If your function have an infinity, you still can partition, because partition is happen inside the domain. But when you take supremum of fx, what happens? The length of your rectangle will fill up. The length of your rectangle. Sorry? It will go infinity, right? Okay. So that means your upper integral will maybe equals to infinity. But what happens to your lower sum? There are two possible cases. Your lower sum may be finite, or your lower sum may be also infinity. Okay. So if one of your lower sum is finite and your upper sum is infinity, that means they are not equal. LF and UF is not equal. Then you will get something not integrable. Okay. But if both of them are infinity, both of them are infinity, huh? Infinity equals to infinity. How to check? I don't know how to check. It's not a round number. How to check two infinity is the same. Okay, we also don't want that kind of thing to happen. Okay, so that's why our condition just fixed to boundedness. Okay. Because we can check two numbers is the same. Okay, how to check two numbers is the same? A equals to B if and only if. How to check two numbers is the same? Sorry? Okay, one way is to check is A greater or equal to B and B less than or equal to A, or you check their difference is 0. Okay. But infinity and infinity, how to minus together, and then how to compare two infinity together, I don't know. We never learned the max of infinity. Okay. Okay. Okay, so it's not good to go unboundedness. And later we'll show that this Darboux integral is the same as equivalent to Riemann integral. Okay, let's do some example. So let's integrate some easy example. Hey, what time is it? 1:03. Okay, let's do 2 example and then we take a break, okay? So let's do 2 example. So suppose we look at the integral of a constant function. Okay, let's look at the integral of a constant function. So if fx equals to c, okay, so fix some c in real number, say, for all x in AB, okay, then we want to show that f is integrable. Okay, moreover, maybe you tell me, what's the integral of AB of this function f? Tell me, use your calculus 1 knowledge. Who? Xiaotong? What's the integral of this constant function from a to b using calculus 1? C is a constant function. And how to integrate this? C times b minus a. Good. Okay. So from calculus, you learn that if you integrate c, you get cx, right? And then evaluate from b to a. Okay, but today we will show this c times b minus a using our upper sum and lower sum. Okay, use upper sum and lower sum. So how do we do this? We want to show that f is integrable. What's the definition? How is f integrable? If what? F is integrable if what are equal? 2 things are equal. If Joshua just now said I need to compare 2 things. What's the 2 things you want to compare? What's the name of that thing? So long I say supplement of the lower. What's that thing? Lower integral and the upper integral. Okay. Okay. How to show these 2 things are equal? Sorry. Difference is 0. Okay, you can do that. But what? But we're gonna use this trick here, this lemma here. Okay, we want to show LF equals to UF. Okay, what's the way we can use what way we can use this lemma here? What happens if the left term and the right term is the same? Then we can imply that the middle 2 term is the same. Okay, correct or not? Correct or not? Okay, so if we can make sure the left and the leftmost and rightmost term is the same, then the middle 2 term is the same. Because what we want to get is LF equals to UF, right? Okay. So is it the same or not? What is B minus A in our case? Okay, it's the same, B minus A. But our function is constant, no? So what's the little m and big M here? Our constant function is bounded below by C and bounded above by C. Okay. So since fx is bounded below by C, bounded above by C for all x in AB by lemma, by the preceding lemma, what do we get? We get C times B minus A less than equals to LF less than equals to UF less than equals to C times BA. Okay, so this implies that what? LF equals to UF. And not only this, what else we know? LF and UF is actually C times B minus A. But how do we define integral of ABS? How do you define this? The Darboux integral of F. We define it to be equals to what? LF or UF, which is C times B minus A. Okay. So in this case here, what does it say here? When we compute the Darboux integral of F, what we really do is we just take a rectangle of width B minus A and length C. Okay, for this constant here. Okay, so there's no like calculus one, you need to increase one power and then evaluate that kind of thing. So we really find the integral using the rectangle here. Okay, we use rectangle to find. Okay, so this is the rectangle of let's draw it here. Rectangle of length C and width B minus A. Okay, how do we get this rectangle here? Because we have our function that is like a constant function here. Okay, it's a constant function. Does it make sense? Okay. Okay. Okay, depend on where is B and A, and then you will find yourself either on the left or right on the interval that contain 0. Yeah, depend. Okay. Make sense? Does it make sense? Okay. Any question or not on this example? Any question? No? If not, maybe we just take a break here. So let's take a break here. We will resume at 1:20. 1:20. By the way, I bring something. You can share. 开进去，开进去。
说要号召大家一起团结起来，迎接这一次油价太夸张了。
谁抵制？
工商
怎么工商跟你有关系？哦，
那个经商，供给比大，供图太激进了。
没有，我怕那个好像是应该是老板把钱吃掉，我觉得。不知道他们讲的啊？
还是亏空？
亏空？
屏障
啊？怎么说？说说看。
就是你说那个呀，就是你说的，他们把钱吃掉了。政府钱追不上了，就要拿点其他地方来用。
对。啊？哦。哈。哦，OK。全部上完。 哪个？这个啊，叶子在下面，你介绍完过后啊，对，没有，就说为什么你介绍我这个就停了，我只是要你后面听下吧。
哦，我就
就这样把它在那个
一个个讲。
没有一个其他的跟我们一样吗？
没有巨人了，
好像有一点不一样。
没有人
很好，你每一个 action 都解释为什么要放这个 action。然后现在我只是说，我的话就是把它完整化，就是说把他们的 action 跟我们的 action 放在一起。可能有些它的某一个 action 都是可以放在一起的。好像可是加跟乘不是另外要做的，你这些应该推得出加跟乘。为什么他们没有介绍加跟乘？看到没？但他们是会这样意思是这样。啊，你看看他们有没有翻一下的，然后看看有做的方式帮我放出来。哎，他们的数是加不起来。是其他的应该 OK 了。啊，是你这个没有放钱的。那这个一应该没有加的，这个我放的没有放钱的方面。然后少一点，就是比较美了，你看，比较美，颜色。
那我需要
假的啊，不用，你只要口碑就好，你只要就总结这样。
还有加跟乘的东西
啊，
就是更没有写出来
啊，对。
那个
还有前面这5个好像有一点跟我们的不太一样，我们看一下能不能从你的推动我的，还是我的点这样 OK， 已经。那如果你做到那个，你最后就把这边有，最后做完了，这边已经很好了，这边已经写的很好，会顺很顺，这样顺。Yes， 没有，你也好讲，就是说要 refresh 吧。哦，因为这个形式是像书里面的，对不对？我是说你去参考一下。I mean，可能你加你自己的字，或者你就排列跟他改一下。你去看一下我写的方法，我没有这样写吗？我写的是啊，也可以吗？都可以啊，对啊，对，就尽量不要跟人家越不一样。所以反正
哦，他现在打出来哦，他这里给过我那个打出来，对，我改了再给你看，对。不是那种子，
什么？
不是那种有点
啊，没错。如果你换题目，
不是那种有点，这是我表达性自己去说的，是，我写的有写的，
不要，I mean，那你怎样把它表达出来？可以啊，什么都可以，只是说你要放到做什么？你放过中一点，就是那样咯，就看写他周末后来会讲到那个东西，然后你就讲那个东西，对吗？啊，
好像很难做那个，
为什么？哪里难？他也没有写到很复杂
看不懂
啊，看不懂那个东西才重点，你要拿来研究一下，把它看懂。你拿来我们一起看，我们可以看懂啊？讲。
因为你看不懂的那个 part 就是你一定是在那边 part 写不好了，我们就把它看懂了。
原来一些 notation 不做啊，感觉很奇怪。
可以，I mean 你理解了，可以用你自己的 notation 其实。啊，你等一下再看，等一下啦，等一下给他下课的时候啦，去 office 研究哦。I mean 多讨厌，有3分钟没有？我给你们3分钟啊。忘记了，我也忘记了给几分钟。
5分钟
啊
？5分钟嘛，
5分钟。
然后我要讲，我问的是那个，刚才是theory嘛，他一开始是那个很多做出来这样嘛。
对。
虽然它是算是 summarize 然后包括 define 它的，
对，
之前已经有 idea of set 然后没有这样严格 define，然后是set theory 它是和那 continue hypothesis 有关系。
OK。
它和 analysis 的那种，我要 make 个 real line 短的 geometric curve 什么这样东西的。
我觉得讲一种就好哎。
因为对，就是很多，所以我不确定要讲哪一半。
就讲一个重点就好了，你的文章里面 contain 一个重点就好了，不要 contain 太多重点，不然会分散那个注意力。就是专心写一个重点就好。你可能可以在introduction 的时候 mention 一下，但是你后面的重点写一个。
因为我不确定是那个一个 SMT set theory， 因为David Hilbert 他是算是 inspire 那个一个那个什么在开发对，他去做那个 SMT set theory， 是因为之前 set theory 好像有些2个样，然后不确定的是个 SMT set theory 它去 帮助
为什么你需要知道这个东西
？I mean 要 relate to
因为我们 mathematics 的第一 part 是 deal with set theory， 所以已经足够了。如果你能够把 set theory part 讲好就可以了。你如果不要讲到 limit 也不用紧，因为我们第一个 part 就是在搞这些东西，所以你已经是活在 analysis 里面了。我们这个 part 里面，yeah， 如果你能够把，
不David Hilbert他没有做太多在就是比较那种原始 set theory，
他没有做，他只是问罢了。
他有一些关于 continuity，
他的 thesis 是什么啊？他 thesis 不是 set theory 的东西
吗？他有一个是
他 PhD thesis 的。
确定我没有看到 PhD， 不过我知道他有做
可能是另外一个人
的 SM。
他就做 real number XM。
有个。
现在你不是做那个比较好？
但就是没有关系到 set theory foundation。
因为如果你这样子说的话，确实是给我想想啊。因为如果其实你要做，可能 von Neumann 的 PhD thesis 是 on foundation of math。所以你要介绍 Hilbert， 只是说 Hilbert 把这个问题丢出来。
其实 Hilbert 他有把问题就是 continuity 他有推荐啦。
OK。
但是
是这个东西 inspire axiomatic set theory。
好像不是。
又不是
出来了。
已经过来了。OK。对，但是现在我们要拎回哪一个？你的重点是 axiomatic set theory。
因为 set theory foundation
对啊，应该是写这3个人比较好嘛，对不对？如果你做 dimension， 对不对？这个人只是问一个问题吧。
可以这样讲
对啊，所以你可能做其中一个人就好。对啊。
因为我还是想看有一个就是
对，但是就是有一点不连哦，我就这样跟你讲哦。如果写的不好的话，可能我会也没有 penalize 很重，看你讲表达，其实这种东西，yeah。因为我的想法是这样，就是我们推出一个 theory， 然后介绍那个推出 theory 的人，然后我们不会去介绍可能他的老师嘛，这样对不对？对不对？这个概念嘛，就是我们就讲主角就好啊，不要讲主角，就肯定是他 inspire 的，但是问题就是来，懂吗？
这里边自己比很多好像是有，就是 I mean 他虽然是去教他去做 set theory，有好像是 他觉得那个 set theory 他一开始提出来是对的一种好的方法，或者是怎样，然后过后为他的 support 或者是
那你就讲 Hubert 推出来的 set theory 咯，也可以的吗？
不算是他推出来的，
嗯，
写那个 set theory 出来的那是偏道主，所以
所以到底谁啊？我其实不知道，所以你要找一下跟我讲他们里面的啊，
因为好像是偏道推出 set theory 的。然后过后可以不强烈死的，是吧？
你去找看，
呀，
你去找看，呀。所以我的 I mean 我已经跟你讲了，我的 idea 就是说，如果你要讲那个 theory，我是说你就是直接讲那个主角，你不要讲主角以外的人，你懂吗？我现在知道你的concern在哪里，你的concern是我要做 set theory，我也要做 Hubert，但是 somehow 这两个又没有直接联系，除非你能够找一个直接联系，这样就可以哦，不然的话就有点牵强啊，这样子讲啊。不是讲完全没有关系，就是牵强，OK 吗？呀，它是这种东西很 subjective 啊，就是看你怎样去表达。其实，就是你希望你能够把它弄到不牵强哦。如果还是牵强的话，
是5分钟是吗？还是
没有这么久哎。
Okay, how long is the presentation? I put there 3 minutes. 3 minutes plus 1 minute plus 2. So it's actually 3 minutes. Oh, plus one. Okay. So it's a 3 minute plus 1 minute presentation plus 2 minutes of Q&A. So 3 minutes is like so last time you have 1 minute only, right? So this time you have 3 minutes. So 1 minute. Last time my experience with you guys is like 6 slides. About 10 minutes you use 1 slide. I mean 10 seconds. So at most I think you just can only go to 18 slides at most already. Yeah, at most. Yeah. And then so this 1 extra time is not how to say, it's not exactly free for you. Okay, if I think that your talk is too long, I will just cut it at 3 minutes because we don't want to waste time. This 1 minute is because maybe you talk about something interesting or maybe you detour a bit then I'll give you extra time to explain yourself. This is the point of the extra time. Okay, no? If not, it's just 3 minutes. Okay, and then yeah. Okay or not? No question? Make sense or not? Make sense? Okay. Yeah, good. 我们等一下再讨论。Okay, yeah. Okay, yeah, let's continue. Okay, so just now I give you an example of integrable function, right? So let's see, there's another function that's not integrable. Okay, so integrable, you need to show that UF equals to LF. If it is not integrable, then what do you need to show? Sorry? Yeah, LF not equal to UF. Okay, very simple. Negation, correct or not? Negation of the statement. Then this function is not integrable. Hey, what function is this? Can you imagine? Imagine this function or not? 1 in the rational place, and then 0 in the contradiction. Okay, here. 0 if x is not rational. So meaning what? Irrational point, this value is 0, nothing. And then only pops up when x is rational. So there's a lot of value 1 point here. Okay, and also a lot of value 0 point. Okay. Actually, there are more 0 point than value 1 point. Have you guys learned countable, uncountable? Got learn discrete math. So I think you should know that Q is countable and irrational is uncountable. So you see here there's more 0 point than 1 point. Okay, and then we want to show that this is not integrable by showing that LF not equals to UF. Alright, so we want to show that LF not equals to QF. What is LF and QF again? Okay, very good. 1 hour already, so we need to do revision. So what is LF and QF? LF is what? Ink or soup? Soup of what? All the lower sum. Okay. UF, ink of all the upper sum. Okay, good. So you need to consider ink and ink of what? Ink of upper sum and soup of lower sum. So meaning you need to study all the upper sum and lower sum first. Okay, so we have to first study all the lower sum and upper sum first. So let's consider any partition. Okay, consider any partition of, let's say here we use 0, 1 in this case, right? So let's just consider partition of 0, 1. Okay, so Tn is 1, T0 is 0. Right. So, I mean, we want to consider what is LFP, for example. LFP. Okay. LFP defined as what? Sum of increment of fx where x live in where. So in this case here, we have Ti minus 1 to Ti, right? Okay. So here we have Ti minus 1. Here is comma, not minus 1. I going from 1 to n. Correct? This formula. Okay. So in every interval like this, Ti minus 1 to Ti, what is the increment of f? What's the increment? What's the increment of f? F only 2 values here. If it is increment, you need to pick the smaller one, right? So the smaller one here is 0. Do you always beat 0 or not? Increment of fx. Why? Why? Sorry, say again. Everything smaller than 0 is not in the domain. No, this 1 and 0 is the codomain, right? Is the codomain. Okay. This is an increment of your image. Okay. So my question is why this increment of fx is always 0. Okay. So you need to ask yourself where you consider this Ti minus 1 and Ti. Okay. So do you reckon that these two are real number? These two are real number, right? Okay. If one of them is irrational, then you achieve the 0. Okay, if one of the endpoint is 0, if one of the endpoint is irrational, then you will have fx equal to 0. But if this two endpoint is not irrational, right? Can you still achieve 0 or not? Inside this interval, can or not? Why? Every two real number you can find a rational and a irrational. Okay, so there might be an irrational number hiding inside this interval here. So you can achieve the value 0. Okay, so in this case, for any partition, any interval Ti minus 1 to Ti, you will find irrational number. Okay, so the increment is always 0. Okay, so you get sum of I 1 to n 0 times Ti minus Ti minus 1. Okay, which is just 0. Okay. How about UFP? Do you want to guess what happened to UFP? It's always 1. Why? Correct. You can always find a rational in between Ti minus 1 and Ti. So the soup of Fi is always 1. Okay, so the soup of fx is always 1. Okay, but what is this sum here? Summing from ti minus, so summing from I equals to 1 to n of ti minus 1. What is this sum here? You reckon this sum here? This is exactly just Tn minus, should be T0 and T0. Correct? All the middle term are alternating plus and minus sum. Okay. Or last time we called it a telescopic sum, right? Okay. So we just left the last point and the first point, which is just, in our case, it's just 1 minus 0, which is 1. Okay. But you see, this UFP and LFP, the P we consider is random P, any partition. So meaning what? Meaning LF is the infimum of set of LFP for all partition P. What's the element in this set? What are the elements in this set? What can LFP be? 0, always 0. So it's the infimum of the set 0, which is just 0. UFP, UF. What are all the I think LF is supremum, UF is infimum. So what is the set of all UFP? 1. Okay, so there's only one thing inside that. You will be always 1. So I confuse the soup with in. So you just get infimum of a set of 1, you just get 1. Okay. So they are not equal in particular here, because 1 is not equal to 0. Okay, we go back to week 1. So f is not integrable. Okay. So in general, maybe the partition is a bit tricky, so you need to be a little bit smart. Okay. Okay, good. So stop here. So so by definition, okay, let's recall f is integrable. Again, I ask you the 3rd time or the 5th time. When is it f integrable? Okay. Sorry? Lower integral equals to upper integral. Okay, lower integral equals to upper integral. In other words, soup of LFP is equal to the inf of UFP. Okay. So you see, we formulate it using soup and inf. Remember that soup and inf, there's a formulation using epsilon. Okay, there's a formulation using epsilon, right? So when they are equal, right, that means what? I can make LFP and UFP epsilon close to each other. Okay, I can make them epsilon close to each other, correct? For every epsilon, if I can do it. Okay, so let's see. I will put down this theorem here. So theorem. This theorem, we call it an integral analytically. So we use analytic method to check whether a function is integrable or not. Okay. So when you see analytic, you should hope for epsilon. Okay. So how do we put epsilon into this story here? So again, we start with a bounded function. Then f is integrable if and only if for every epsilon greater than 0, there exists a partition. Okay, give you an epsilon, you need to choose a partition for me. Such that what? Such that UFP epsilon minus LFP epsilon is less than epsilon. Okay, I can make the difference between upper sum and lower sum really small. Okay, if my function is integrable. Okay. Any idea how to prove this? Or at least which direction you think is easier? Left to right or right to left? Remember that integrability, you need to show UF equals to LF. Okay, so which direction is easy, you think? Right to left. Yes, right to left is easier. Okay, do you have an idea how to prove it? Do you have an idea? Any idea how to prove this? Do you have any idea? Sorry? Equal to 0. Prove that. So I want to show that UF equals to LF. Okay. Any idea? Yes. Correct. Yes, that's the goal. Okay, so yes, that's the goal. So our goal is we want to show that. Our goal is to show that the difference of UF and LF is less than epsilon for all epsilon greater than 0. Yes, that's right. Okay, so this is our goal. How to achieve this goal here? How to achieve this goal here? UFP greater than. Okay, so if I want to show this, so let epsilon greater than 0 first, right? So we just fix 1 epsilon, and then so you want P, right? So we can choose P epsilon. This is by assumption. We can choose P epsilon such that U F P epsilon minus L F P epsilon less than epsilon. So this is how we choose this. This is by assumption. Okay, so this part is by assumption. Okay, then how is this difference here? Okay, how is this difference here compared to this UFP epsilon and LFP epsilon? How does this difference compare? Remember that last time we have a lemma, right? By lemma, which lemma? By previous lemma. Can we compare this UFP epsilon, UF and LF and LFP epsilon? That lemma not useful, right? Because that lemma is dealing with a particular partition, the whole interval in particular.
So in this case here, what can we see? How do you compare UF to UFP epsilon? Least upper bound, right? So UF is the least upper bound, is it? Greatest lower bound, infimum. So UF is the greatest lower bound of all the UFP. So that means that UF should be less than or equals to UFP epsilon. Correct now? Okay. And then LF, leh? LF have to be what? Greater or equals to LF epsilon. Okay. Because LF is the lowest upper bound. Okay, upper bound is enough already. Okay. So UF minus LF is what? Less than or equals to UFP epsilon and what? Minus what? LFP epsilon. But we know that the difference of these two, UFP epsilon and LFP epsilon, is less than epsilon. Okay, so we have proven that UF minus LF is less than epsilon. Does it make sense? Make sense? Does it make sense? Okay. Okay, so since this is true for all epsilon, what is the number that can be smaller than every positive number when it is positive? Just 0. Okay, not positive but non-negative. Okay, it's 0. So this implies since epsilon greater than 0 is arbitrary, UF equals to LF. Okay, or before that, you maybe get U modulus of UF minus LF is 0, and then you implies that UF equals to LF. Okay. Okay. Any question on this part? This part should be straightforward. If it's not straightforward, please look at it again, and again. Okay. Again and again. Okay. How about the other direction? Okay. So assume f is integrable. And then want to show that. Okay, what do we want to show? Want to show that for every epsilon greater than 0, there exists a partition P epsilon of A, B such that UF P epsilon minus LF P epsilon is less than epsilon. Okay. So your job is what? Give you an epsilon, find me a partition. Okay, find me a partition. Okay, so what can we do here? Remember, U is what? U is infimum of something. L is what? Supremum of something. Okay, infimum of something or supremum of something. So fix an epsilon greater than 0 by the definition of LF and UF. Okay, what do we get? There exists some P epsilon A, maybe P epsilon B, for example, such that, okay, such that what? Such that LF of P epsilon over 2A is greater than the what? This is the supremum. So greater than the supremum of lower sum minus epsilon over 2. And you also can find U of F PB epsilon over 2 is less than UF plus epsilon over 2. So the first one, what we have used the supremum property. The second one, we use the infimum property. Okay or not? So the element on the left-hand side here is the element where we consider the infimum and supremum form. Okay? Make sense? Okay or not? Okay. All right. So, I mean, how can we put these two things together? We can simply take their difference, for example. Okay. So then U of F of P epsilon over 2B minus L of F of P epsilon over 2A is less than UF plus epsilon over 2 minus LF plus epsilon over 2. So that's why we pick epsilon over 2 here, because we want to make it into epsilon. Are we done? Done or not? Done or not? Huh? We are not yet done. You know why? Because what we want to show is there's one partition that works for this inequality here. But the partition we use here is different for two of them. One is coming from the UF, one is coming from the LF. Is there a way to find a uniform partition for it to work or not? What do you think? What do you think? Yes, we can simply set P to be the union of P epsilon to be the union of two partition here. Why? The new P here is a refinement of the two, right? Correct or not? So since it is a refinement of the two, meaning what? U of Fp epsilon minus L of Fp epsilon have to be less than U of F less than or equal to U of Fp epsilon over 2 minus L F of P epsilon over 2A. Correct or not? Because when you consider the refinement, the upper sum decrease and the lower sum increase, so their difference will become smaller. Make sense? Okay, because PE is a refinement of P epsilon over 2B, and then PB is also a refinement of P epsilon 2A. Okay, so the technique in this whole chapter is whether you know how to do refinement or not. Okay, how to do refinement? Just take union, or you can add points into your partition. Okay, so the technique in integration you must know to get out from this course is to do refinement. Okay, you must know how to do refinement. Okay, so far, any question? Okay, if not, there's a corollary here. So you see epsilon already, right? For all epsilon, this is true. So you can phrase it in a limit way. Okay, so Jinsen, this is the limit statement that I'm trying to say just now. So let's say this f is integrable. Okay, then there exists a sequence. Okay, sequence of Pn of partitions. Okay, so these are partitions. Obviously, is for AB, such that the limit when n go to infinity, the UFPN minus LFPN is equal to 0. Okay, so how is this a corollary? So just now I tell you that for every epsilon, I can find a P epsilon for you. But here got a sequence of. So how to find this sequence here? I guess you can fix your epsilon to be 1 over n. Okay, so for every 1 over n, you can find Pn such that the difference is less than 1 over n. And then you can show this limit. Does it make sense? So my proof idea sketch is set epsilon to be 1 over n in the preceding theorem. Okay. Because for every epsilon, the previous theorem will send you a p epsilon such that the difference is less than epsilon. Make sense or not? Okay. So finding question. Okay, if no question, right? Okay. Later, now we will do 2 examples. Wow. 时间过得这么快。Okay. So let's do 2 examples. One, I will try to integrate linear function. And then second, I'll ask you to do exercise on integrating quadratic function. Okay. Let me show you how to integrate a linear function. So just now we integrate constant function, right? Okay, we will use this theorem to integrate linear function. Okay, so let's do one example first. And we will show that if fx equals to x, then first of all, f is integrable, and then and let me ask you, what's the integral of f from a to b? In this case, what's this integral? From calculus 1. Over 2. Okay, good. So now we will show this number using the partition way. Okay, we use the partition way, the integral, the Darboux integral, the upper sum, lower sum to compute this number. Okay, let's see how it works. So I mean, in your mind, right? You should have this function appearing in your mind first. Then it's easier to do stuff. Okay, so let's imagine this line here. Okay. And then imagine we want to integrate it from sum A to B, like this. Okay. So using the Darboux sum, meaning we need to put some rectangle. Okay, so we need to put some rectangle here. I mean, we start with partition first, correct? No? Okay, and then we consider the lower sum and also the upper sum, like this. Okay, does it make sense? Okay. All right. So we are trying to use the theorem just now. Okay. So the theorem just now, how to show f is integrable? If and only if for every epsilon, okay, you can find partition p epsilon such that u p epsilon minus lf p epsilon is less than epsilon. Right. So how to do that? So how to do that? Sorry, fix epsilon first. Good, very good. So let's fix an epsilon first. Fix epsilon. Okay. Then how? Hey, Roland is not here today, right? Roland. Anyone know where is Roland? Okay, that's fine. Okay, so how are we going to do this? How are we going to do this? So let's think for a moment. How are we going to do this? Right. So is any how to say any uniform way to cut this interval or not? Any uniform way to cut this?
You know what is uniform where? Meaning I want to cut it into an equal length. Okay. Any way to cut it equally or not? B minus A over N, okay? That's very fair, right? B minus A over how many points you want to introduce it in, okay? So, how to pick this N? So, okay. So, maybe we just cut it first. Okay, let's cut it. And then later we'll show that this is the N we want. So let's cut it. So let Pn to be, let's see. So let's be Tk equal to A plus K times B minus A over N, such that K is in between 0 and N. Okay, so let's check. Okay, let's check. Does this formula give me a partition or not? Okay, let's check it. When K equals to 0, what happened? It is just A. Okay. When K equals to 1, A plus B minus A over N. Which means what? The B minus A over N is the length of your that you divide your intervals into, right? So the length here is B minus 1 over N. Make sense? Okay. So what's the N times you add this N? What's the N time you add this length? You should get B, correct? So when you sub K equals to N, so you already add up all the length inside your partition, you should get the last endpoint, right? So N over N is 1, and then A plus B minus A is B. Make sense? Okay. Anyone confused? Anyone confused? Okay. So this is for every N. Okay, good. Yes, question. Okay, I'm being stupid here. So should be N, and should be K is greater equal to N, and then K is less than equal to let me check. Equal to N. Okay. So you cut your interval into N equal parts, and then you need to add it back to get the whole interval. Make sense? Okay. All right. So let's later we want to see how it works for epsilon. Okay. Okay. Right. So if we already cut into N equal parts, right? So okay, maybe I make a comment here. So we partition AB into N equal length. Okay. So I make a comment here what we are doing. Okay. So in this case here, what is sup of fx such that x is in one of the interval? What's the sup here? What's the sup here? Huh? What's the sup here? From this diagram, right? If you fix one interval, okay, tk minus 1 to tk, where's the sup? Where's the sup? Huh? It's exactly ftk. Okay, it's exactly ftk. Very good. So it's exactly ftk. So what is ftk in this case here? What's the formula of tk? It's simply a plus k times b minus a over n. Okay, so this is the supremum. How about infimum? It's similar, right? What is infimum here? Tk minus 1. Good. So the infimum here is ftk minus 1. But what is ftk minus 1? It's simply a plus
k minus 1 over n times b minus a. Okay. So in this case here, we are good. Okay, we are ready to compute LF, PN, and UFPN. Okay. So by formula of LFPN, what do you get? Inf of fx. Correct? Yeah, correct. So where do we use k? Okay, we use k, sure. So we have a k equal to 1 to n, where this infimum is going from tk minus 1 to tk, and then times tk minus 1. Okay. So what is this thing here? We get the formula of inf already, right? So inf is literally just a plus k minus 1 over n and b minus a. Like this, okay? Times tk minus tk minus 1. Okay, good. So how to compute this guy? Any idea to compute this guy here? So I mean, those that doesn't depend on k, we can put it out first, right? Okay. Any guys that doesn't depend on k. Sorry, b minus a over n, right? Okay. So I mean, I guess one way is we can split this sum here. So can you see what sum I want to split? I can split this two sum first because a doesn't depend on k. Okay. So maybe I split the sum like this first. So a times tk minus 1 plus the sum of, okay, so just now we said that b minus a over n doesn't depend on sum, right? So I pull it out. So I have this sum here. A minus 1 times tk plus tk minus 1. Okay, but what is this sum here? So for the first part, a is a constant. Okay, so you are summing all the tk. So this is a telescopic sum such that it is b minus a. Correct, no? Okay. How about the other part? This part a bit tricky, a bit tricky. How does this work? How does this work? Any idea how does this work? Sorry. For the other sum, k minus 1 of this difference here. How does this work? How does this work? Mm, mm, I mean, we can split further first if we want. Okay, we can split further first, such that we get minus of b minus a times b minus a over n. But how do we deal with this extra bit of k times tk minus tk minus 1? Wow, how do we deal with this last sum? Anyone have any idea? Sorry? What Zhangtai? K equal 1 equal 2 and then what can we see? Okay, let's do some experiment here. So what's this guy? This guy is first of all t1 minus t0 plus 2 times t what? T2 minus T1 and then plus 3 times T3 minus T2 like that, right? And then all the way up to n times Tn minus Tn minus 1. Okay, so what happens here? So what happened is, what do you get? For T1, what do you get? Minus T1. For T2, what do you get? Minus T2, is it? And then for the last term, there's no 1 minus with Tn minus 1, right? Correct or not? So do you just get n of Tn minus Tn minus 1 minus all the way out to minus T0? Is this the sum you should get? Seems like it. Okay. Okay. And what is this? What is this? What's this? It looks a bit weird now. What's this? Hey, why calculate until something like this? Hey, why calculate until something like this? What's this thing? Sorry, I only know Tn to be B, and then T0 to be 1. Sorry, A. And what's this middle guy thing doing? So weird. Any idea? Any idea or not? Yes. Yes.
The sum from 1 to n minus 1 of tk itself.
Say again. So what are we trying to do here? What are we trying to do here? Sum of which sum here? This sum here?
Not including p minus.
Okay, sure. So let's deal with this sum. Okay.
Equals to ntn, which is mp.
Correct.
The sum
Yes.
from 0 to n minus 1.
So the sum of, minus the sum of equals to 0 n minus 1 of tk, correct? Sure.
tk is defined.
Good. So what's the formula of tk? Very good. tk, the formula is what? A plus 1. K minus K times B minus A over N. Okay, but what is this sum? Obviously, you have NB minus N minus 1 times A, right? Because A is a constant, you add N minus 1 times. But I think the trouble should be this guy. So what's this sum? B minus A. Yay, what's this sum here? Sum of K times B minus A over N. Okay, this sum actually is not too bad. So we pull the p b minus a over n out of sum of k equals 0 to n minus 1 of k. What's this sum? Sum k from 0 to n minus 1. What's this? Actually, it's just summing from 1 to n minus 1. So what is this? What's the formula of summing integer from 1 to k? N minus 1. I think it's n minus 1 times n minus 2 over 2, is it? What's this formula? Is this true? Huh? Sum of number from 1 to n minus 1. Correct. N minus 1 times n minus 2 over 2. Is it correct? True? Okay, good. Okay, wow, we've gone a long way to get this number here. So how many things we got here? So let's organize. So let's keep this at the side. Okay, let's organize. What do we have? First term, we have a times b minus a minus b minus a times b minus a over n. So we just put it as b minus a squared for n. And then what? And then we get new nb. Okay, nb. And then we get minus n minus 1a. And then we get n minus 1 times n minus 2 over 2 times b minus a over n. Wow, we get quite a lot of things. Can we stop here? Maybe we can stop here. Can we stop here? Let's stop here then. Do you want to simplify or not? We simplified it. Maybe we just keep it here. Okay, let's keep it here. Okay, let's keep it here. Can we keep it here? Yeah, question? Where? Plus NB. Sorry? Minus NA, where is it? Where? Uh-huh. Oh, correct. Okay, you are right. So it should be NA, not N minus 1A, because we sum from 0. Okay, good. So it should be NA. Yes, you are right. Okay. 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 Okay, good. How about U? UPN is another long story already. So what is UPN here? So the difference here of UPN is what? Is simply the part where you substitute a plus k minus 1 over n of b minus a to be k over n. Correct or not? You consider the supremum. So you consider the right endpoint of your subpartition, subinterval. Okay, subinterval. All right. So should we do the same analysis here? I think it's better we keep the same analysis. Otherwise, we will get different number out of the two. So in the first term, we also should get a times b minus a. Correct or not? If we split out this a here, okay, we should get the same. So the difference here is we no longer have the minus 1 anymore. We simply just have this part here, k times b minus a over this thing. But this thing we computed, right? This is this guy here, the long guy. Correct or not? Everyone see? You see? The second sum here is simply the very hard sum that we computed just now. B minus A over N times K. Okay, correct? Everyone agree? Or should I make it smaller a bit like this? Okay, can everyone compare? Can compare or not? The second sum in UFP is actually the hard thing that we computed just now. Agree? Everyone agree? Okay. So, meaning what? So the difference we get is actually this term here. Correct or not? Because the top and the bottom is the same. Okay, same sum. So maybe I just put here plus NB minus NA minus n minus 1 times n minus 2 over 2 of B minus A over N. Okay, so what's the difference between these two? So you can see that UPNF minus LPNF, what is it? They really only differ by this term. Can everyone see it? Or not? Okay. So the difference here is this minus 1 here, minus 1 bit here. Okay, and then this minus 1 gives the sum of minus B minus A square over N. Okay. So the difference here is really just because minus minus become positive, so you get B minus A square over N. Okay. So for every epsilon, how do you find the N that works? How do you find the N that works? So how do you fix it? So we want to choose N such that N is greater than epsilon over B minus A squared. So that this thing will be less than epsilon. Correct? Okay. Yeah. Okay, so for every epsilon, I find this Tn. Okay, I need to make sure the N is many enough. So how many is enough? You take your epsilon, divide by the length of your interval square. Okay, then it will be enough. So this is good. So therefore, f is integrable. Okay, since f is integrable, how do we find the books? How do we find the books? Books integrable. How do we find it? A function is integrable if what? Lower sum is equal to the upper sum. Okay, so you just need to find, if the lower integral equals to the upper integral. So you just need to find one of them. Okay, so you prefer lower integral or upper integral? Lower integral. Okay, sure. Let's go look for the lower integral here. Okay, so for lower integral, you need to find what? You need to find the supremum. Okay, so how to find the supremum here? Supremum of this LFPN. Okay, how to find this supremum here? So if you look at this LFPN, did you recognize a thing here? What did you recognize? Can you recognize that this LFPN is increasing or not? Seems like a bit hard to see. Can you recognize that this LFPN is increasing? Increasing. The increasing? Yeah, when n goes to infinity, yes. Is it increasing or not? Why? You see, our first term is constant. Okay, don't move it. Second term is not constant, but when n increases, the term decreases. So you're taking less difference. Okay. And then NB increase. But B is greater than A. Correct now. Okay, so I mean, okay, let's combine this. N times B minus A. Because B is greater than A, so this guy is positive. So N is increasing. How about the last term here? Last term here a bit tricky. Last term here, how to study this last term? So we need to rewrite, no? Correct or not? We learn limit, right? So let's rewrite this term here. So we really should get 1 minus 1 over n and 1 minus 2 over n. Okay, but what is this limit here?
this limit here should go to 2 over 2. Okay, 2 over 2 is 1. So 1 times b minus a should be just b minus a. So meaning what? Meaning the difference here should be also getting smaller. The number that we're taking difference here should be also getting smaller and smaller. Okay, so the both negative term is getting smaller and smaller. So the whole sum is getting larger and larger. Does it make sense? Make sense or not? Make sense? Any question? Okay, so this partition is actually increasing. Okay, so so what? So I mean, because LF as this, right? Okay, LF as this, and then this is a sequence that converge. I mean, sequence that converge. Yes, sequence that converge should converge. Okay, they should converge to the same limit. Okay, same supremum. So we can consider the limit of this lower sum. What's the limit of this lower sum then? So let's write. So this one should be equal to LF, and then this should be equal to limit of n go to infinity of L F Pn. Okay. Since L F Pn is increasing. Okay. Okay. And if this set have a suit, that should have the same limit. They have the same limit. Yeah. That is increasing. Then this thing is equals to what? Equal to this guy here. Let's bring this guy down. This guy here, this guy here. Okay. 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 So what's the limit of this thing? Okay. Finally, what we get is a over b minus a, and wait, there's an n here. A bit crazy, huh? Isn't it going to infinity then? Why is there an n here? Let me see. Are we doing something wrong? Did we do something wrong or not? Wait, let's write down the second term here. Okay, what's wrong here? Why there's a term like this? N times b minus a. This term, if exists, this term should go infinity. What's wrong with it? Can simplify? How to simplify? How to simplify? How to simplify? Sorry, Sang. Did we do some wrong calculation? Yellow part, Sorry, NB minus NA, and then minus this guy, and then what do you mean positive? NB minus NA, and then minus this guy equal to what? Okay, so are you saying that we try to do factorization? Okay, so let's do it here. Okay, let's try and do factorization first. So what do we get here? So I mean,
So let's combine them. So if we combine them, what do we get here? So a of b minus a minus this guy is still the same. And then if I combine them, what do we get really? So I get plus b minus a times n minus the whole thing. Correct or not? This whole thing here. So, over 2. Just like this. Just now I pull this 1 over n. So I mean, I take 1 over n and then divide here. Did I do wrong division? All right. Let me see. No, right. N square. Oh, you are right. You are right. You are right. You are right. True, true, true. True. Very true. So, so should I return it? True, you are true. Or let's put it back first. Okay. Let's come back here. Let's simplify again. Oh, you are right. You are right. N minus 1, n minus 2. Okay. So, put it back. Here is n. Okay, good. So here also should have an n here as well. And then we're going to simplify some more. Open the expand. Okay. Okay, so let's expand it. So how do we expand it? Can we do this computation first? So this one is n squared minus 3n plus 2, is it? Okay. So we have 2n minus the whole thing here. So we should get minus n squared. And then minus 2n minus 3n should be, oh sorry, my 2n plus 3n, so it should be 5n. And then minus 2. Like this. Okay, run check together. Yes, okay. Do we want this? N minus 2, 1. Cannot factorize anymore, right? Cannot. Okay, cannot factorize. So what should we do? I'm not sure is this leading to something because different calculation in my notes. Should we factorize again? Should we factorize again? Are we okay to compute the limit already? Let me think. D over n squared. What's this limit? Should we combine everything actually? Seems like it. Or how about let's continue? Wow, this computation quite long. And let's put it out. So let's put b over a over n out so that we get b minus a over n. Sorry, just b minus a minus b minus a and minus plus
plus minus n squared plus 5n. Getting a bit crazy at this calculation. What's the part of mistake? Let me think. You managed to calculate anything, Larry? You use upper sum and then you got it. What do you got it? What have you got? Let me see first. If can, then just share me the calculation. Seems like work on. Can you share me to Teams and then I can share it here. Well, what's wrong with this? Lower sum calculation should work, eh? Here. Have you sent me? Okay. What's wrong with this sum here? 2n minus 2, 5n minus 2. Get very ugly. Mathematics shouldn't look like this one. If get ugly, something is wrong. Why is it so ugly? Some factorization wrong. Have you sent it to me? Maybe see what's the upper sum calculation, and then we can check. Yes, got it. Send me. Right. So let's see what does Larry send me here. Okay. Okay. Let's see what Larry sent me. Okay, let's look at this one. Okay, he used UFP instead of LFP. He also got this ND stuff or NA stuff also got, right? It's the same thing. Hey, but here is the different formula. Why is the n minus 1 over 2? I thought it's n minus 1 times n minus 2. Formula is what? N times n plus 1. We used the wrong formula just now. Correct? And then? Okay, so the question is, the formula is n times n plus 1 or n times n minus 1? Which one? N times n plus 1, right? I think this one is the Gauss proof. You know, Gauss proof to his, I don't know, primary school teacher or secondary school teacher. How to add 1 to 50. The Gauss proof. Okay, so actually we have a wrong calculation just now. It should be n and n minus 1. So let's say if m and n minus 1, how does this sum work? So let's go to the next round. So you just expand on. Okay, right, sure, just expand. And then after that, just do normal limit trick. You just divide n squared throughout. And then what? Okay, so the 1, 2, 3, 4, last 4 steps we are going to take limit already. Okay, so when you take limit, there's only one term involved n here, 1 over n. So what do you get? You get this whole term here. So you get 3 terms here. A times b minus a from the first one, b minus a squared from the second one, and then the third one, the last guy here becomes what? 1 over 2. Okay, so becomes divided by 2. So then you simplify. How do you simplify this? So really, this guy here, you left with b minus a squared over 2, right? So you add it to this guy. Okay, a times b minus a plus b minus a squared over 2. What is that? You should get this one, b squared minus a squared over 2. Okay, so this is the calculation you did in calculus 1. I mean, the answer you get. Okay, so from this algebraic plus limit. Okay, algebraic plus. Okay, no? Any question? So just now, where is our mistake? Our mistake, happens when we add the n-1 sum. Okay? We add fewer sum, less sum, so we cannot cancel stuff properly. Okay, make sense? Okay, everyone, okay, happy? Go back, have to change the calculation for LFP. Okay, any question? Any question? I think we should stop here because everyone quite tired already. Maybe I show you. Let's watch the presentation before we finish. Okay. Okay. So we have another example on quadratic function. Maybe we do it tomorrow. Okay, and then we will watch this function as function. There's a video before we finish up today's lecture. Wait. So when you watch this video, right, I want you to I don't want you to comment, but I want you to compare. Okay, compare their presentation skill and then how they react in front of the public. Okay, I want you to be the NVIDIA's boss. Okay, we need to try the NVIDIA boss, and then but you can see. Wait.